So in previous videos, we've been talking a lot about kinematics, joint angles, and how to interpret them, but we haven't really talked about where they actually come from. So in this video, I want to give you some background on how we might calculate different joint kinematics in different contexts. The most simple way to do it is just straight up measure it using a protractor like this. Technical term for this is goniometry. And if you are in the clinic or out in the field, this is likely what you'll be using. You get one of these protractors, carry it around, you can measure flexion and extension. Only problem is you cannot measure anything but 2D angles. So measuring hip internal rotation, for example, is going to be very difficult with one of these. The data that I've been showing you comes from a motion capture lab. So you may have noticed in some of the simulations I show you that there's all of these dots. And these dots are in the original data. We stick them on people so that we can measure where their different segments of their body are. So how this actually works is using a bunch of cameras. If you have seen, I imagine you have, if you have seen videos of like people making movies in Hollywood and they have a green screen and the actors have dots all over them, we use the same technology in biomechanics research. So you might have some person here and you put a bunch of those dots on them. And suppose this person has a reflective dot right there. The cameras in the lab can pick up the location of that dot because they're reflective. I have this image over here just to show you that what these cameras do is they shoot out infrared light that bounces off those reflective dots. And that infrared light can actually get picked up by cell phone cameras even though you can't see it yourself. So if you're in the lab in person, it looks like this. If you pull out your smartphone, it looks like this. So by localizing the three-dimensional position of those dots, what you can do is you can determine, if you put several dots on, say, the shin, you can determine the orientation of the shin in space. And then you can do the same thing with the foot, determine the orientation of the foot in space. And then the joint angles that you care about, say, for example, the ankle angle is going to be the angle between those two segments. So the important thing to remember is that you need, if you want to know a joint angle, you need information on the position of both segments. Let's say you need position of both segments. And by that I mean the segment on either side of the joint. So in this case, the shin, the foot. In our goniometry example, right, we needed the angle. Hopefully you can tell what this is, by the way. This is a knee angle. So you've got the patient's thigh going up like this, hip joints, and they're laying down, and then this is the knee, and then their shin goes down like this. Ankle and foot down here. So notice, by the way, to measure this angle, we need the orientation of the shin and the orientation of the thigh. So by doing that, you can get the joint angle. And the advantage of this term for this is motion capture. The advantage for this is that you can determine the three-dimensional angles. So that means flexion, extension, internal, external rotation, and adduction, abduction. Of course, in the case of the foot, what would be at the ankle joint, what we'd be looking at is really just the flexion, dorsiflexion, plantar flexion of the ankle joint, and the inversion, eversion of the subtalar joint, about subtalar joint axis. But more generally, say at the hip joint, you can easily get all three of these from motion capture data, which is the big advantage for them, and that's why you'll see these in research application. So do you remember from last week when we talked about models and modeling, specifically how complicated of a model do you need? This gets into joint kinematics because suppose we're interested in a motion like the squat. We know that the hip is a ball and socket like three-dimensional joint, but if we're really just interested in squat mechanics, we might be able to approximate the hip as a hinge joint for our purposes right here. So we may only care about, say, this hip flexion angle right here. We may not care so much about the adduction, abduction of the hip, depending on how we're analyzing the squat. Likewise, we may not really care about the subtalar joint angle if we really just care about how much are these squatting shoes elevating the heel off the ground, which is, by the way, maybe some of you know this, the advantage of squatting shoes is that you can, by elevating the heel, you don't have to dorsiflex your ankle as much, so this angle can become smaller. So that model of kinematics might be appropriate for looking at the action of the hip extensors, hip flexors. Notice, however, though, there is an element of external rotation at the hip in the squat and at the hips during the squat. And depending on the application, depending on your particular performance or clinical or research question, whether or not a 2D model like this is adequate just depends on the question you have. When I mentioned that you need both, you need the position of both segments, that leads me to the other point I want to close with, which is that depending on how complicated of a model you need, you may or may not want to think about segments of the body as one thing. So what do I mean by that? Previously, I was talking about measuring the ankle joint angle, and I was implicitly making the assumption that the foot was just a rigid stick and that the shin was a rigid stick, and we could just measure this angle between them. Again, if what we care about is maybe how effective are my squatting shoes, that's probably a fine assumption. But if what we care about is some really particular action about the way the toes are moving, then we need to break the foot up into different pieces. A problem you might often see in clinical settings is first metatarsal phalangeal joint pain. So right there, ball of foot pain, often read MTPJ, metatarsophalangeal joint. To model this, you might want to think about the foot as having the calcaneus here, the talus here, the midfoot, and the toes all moving as one. So in that case, you'd have like talus moving about the subtalar joint, the calcaneus rotating about the subtalar joint. You'd have the talus here. You'd have the midfoot, kind of metatarsals and cuneiforms and navicular and all that stuff, and the toes. Now, you and I in this class won't be doing mathematical modeling of this, but we will be doing what you might call conceptual modeling. So in the context of, say, somebody who's having foot problems, you might be thinking about the subtalar joint. You might be thinking about the midfoot joint, which we haven't really talked about very much, but is a part of the foot that has some range of motion. You also might be interested in the metatarsophalangeal joint, either as one unit, or maybe you're interested in just the motion of one of the toes. So I bring that up only to point out that in this context, suppose we were interested in the angle of the toes we're making relative to the rest of the foot, the two segments we would care about are right here and right here. So you can actually get, if you do clinical work, you can get little baby-sized goniometers to measure teeny little joint angles like this, and you would align them with the midfoot and the toes. So hopefully that gives you some background and useful information on where these joint kinematics measures come from and when we might be interested in them.